All right, so welcome to the Flatiron Institute. It's great to have you here. Thanks for coming. I know that some of you came from far away and arrived as late as a couple hours ago, so thanks for making it here. So I'm just going to give a few kind of intro slides before we jump into the first session. In particular, welcome to those of you for whom it's the first time here. So just to orient you a little bit, we're in the auditorium of the Flatiron Institute. CCA, the Center for Computational Astrophysics, is located here in this building on the 5th and 6th floors. So especially if you haven't been, feel free to take the elevator up there and just walk around and get an impression during one of the breaks or whenever. The Wi-Fi information is here. And more about CCA, I know that some of you have already registered for hanging around at CCA on Friday after the end of the workshop. But if you haven't, and if you are interested in doing that, please let the front desk just outside here in front of the elevators know that they will register you for Friday, or send an email to Christina or to me. And please do so today so that you can be on the list in time for Friday. Okay, so this is our schedule for this week. So we organized the 4 days that we have roughly by topic. So we'll start today with hearing about the large-scale structure. Tomorrow, talks about cosmological inference and the like. Move on Wednesday to galaxy formation and dark matter, and end with forward models, simulations, and emulations, generative models on Thursday. Every day we have 2 invited talks, which will be 30-minute talks, 25 plus 5, and contributed talks, which will be either 15 plus 5 or 8 plus 2. We'll also have discussion session to close each day, and many breaks in between. So that's and 2 receptions, which I'll touch on in a bit. So this is what the week will look like. The timer speakers, you will find a timer here, just in front of you at the top of the back wall. The timer will show the time for your talk, and then the time for the Q&A. So if you're given a 20-minute talk, then it will show 15 minutes, and then it will reset to 5 minutes for the questions. Audience members, when you're asking questions, please turn on your mic, as you just saw in the video. I know it can be a little confusing. It's the black circle. You push it down, and then it goes up, and then the light turns on, and then you know that it's on. Okay. And Zoom participants, please enter your questions in the Q&A. There will be someone who's monitoring them and reading them out loud to the room. And if you have any technical difficulty, also please write in the Q&A. It's also monitored by the AV team. We have a code of conduct. It's on the workshop website. Please check it out. In short, let's all just be respectful and constructive. All right. So the 2 special, or a couple of special sessions that we have. So we'll start. The first one will be this afternoon, the lightning poster presentations. So after this afternoon's coffee break, we will start with that. So I will ask all the poster presenters. We have about 40 posters, to self-assemble right there in that area by first name, roughly. The posters will be presented. We'll have 1 minute per poster. There will be sorted, I think, almost perfectly by first name. So yeah, so please self-assemble there in that way. And yeah, and the posters, if you haven't seen yet, we have 2 monitors. The posters will be rotating on those monitors outside throughout the week. And then we have the printed poster session tomorrow. So that will take place not here, but across the street, directly across the street, at the other building of the Simons Foundation. Also on the second floor, there's a larger auditorium, but we will be outside the auditorium. There's a much larger kind of promenade space outside that auditorium. We'll have room for 40 posters and also a reception. So that'll be the only part which is not right here. If you haven't done so yet, please give your printed posters at the front desk here, either today or tomorrow morning, and they will set them all up for us across the street for tomorrow afternoon. Yeah, we also have a reception this afternoon after the discussion at 5. This will be right outside here where breakfast was, and yeah, just to make clear, there will be breakfast and lunch right there every day, as well as coffee breaks. Any questions? Okay, great. So let's start. Carol, okay. So, and the first speaker, Daisuke, right? So you have this. Can you remove this?
I think I'm worried.
Ah, you have one. Okay, nice. All right.
Yes, so Daisuke is going to get us started. Thank you very much.
Great. Well, thank you very much, and thank you for the organizers for organizing what will likely be a very exciting workshop. And I hope that we can discuss a lot about the future of how to advance cosmology and galaxy formation astrophysics. I would like to start with this topic on how to harness CAMELS simulation. This is a set of simulations that many of you are probably familiar with, which is spearheaded by the Simons Foundation and the coordinators who are sitting here, which really created, I think, exciting data sets. And I'd like to discuss a bit about how we might be able to use this kind of new set of simulations to actually then advance these cosmology and galaxy formation astrophysics in the future. I'd like to start with these pictures of what where we have been in cosmology and galaxy formation. We know that we have an initial condition of universe that's exquisitely well mapped out by a cosmic microwave background, and we know that we have a working model of gravity, Einstein's theory of gravity, some modified version of it, which we can then use computer simulations to then simulate how the structure formation occurs, and then actually describe exquisitely the large-scale structure of the universe that we see in galaxy surveys today. Of course, in this concordance the CDM model, we have some serious outstanding issues. We have a very precise models of structure formation, but we have well, the universe as we know it, of course, is made of things that we don't really know about: dark matter, dark energy, and then that the galaxies that forms in the universe seems to be governed by much of these dark constituents. I would argue in this talk that these little bit of baryons that we thought we know a lot about, in fact, that there are a significant fraction of baryons in the form of warm, hot gases. They are dominant form of baryons. They have been somewhat elusive in so far, and they actually play a significant role in doing cosmology and galaxy formation physics, in part because they would have this thing called baryonic effect. A lot of the things that we are interested in depends very sensitively, especially on small scales, on how well we know not just the composition, the fact that they're there, the missing baryon is there, but actually their properties is extremely important for actually doing precision modeling for cosmology, as well as actually holds the key for understanding galaxy formation physics. That will be my main focus of this, is to see what are some of the interesting future that we might be able to chart by understanding those warm, hot baryons and how that would enable cosmology and galaxy formation physics in the future. The reason why this field is really exciting and in fact the cosmology is becoming increasingly more data-driven is because of this emergence of multi-wavelength survey that are just coming online, ongoing, and coming online, starting from the optical survey. There are many, including Euclid, which was launched by European Space Agency, Roma, which is coming online from NASA, as well as the CIMA Observatory, CMBS-4, next generation CMB experiment, as well as eROSITA, the Russian-German mission, designed to do all-sky survey, have been taking beautiful images of X-ray skies, and then SKA, which is coming online in radio to elucidate something about non-thermal universe in the future. So these huge amount of data over the next decades, we're going to be able to map out the distributions of galaxies and gas, as well as dark matter through gravitational lensing. We're going to be able to map out in detail the structure of formation universe, and these large data set will be giving us significant insights into the cosmology and galaxy formation physics over the next decade or so. And of course, one of the most prominent feature in large-scale structure map is galaxy clusters, the most massive gravitational bound objects in the universe, and you can study those. We have been studying those distribution of dark matter, gas, and stars. You see everything in those massive objects. The future is to go beyond galaxy clusters, going into the cosmic web, looking at smaller mass galaxy groups, galaxies, and cosmic web, filaments, and voids. We like to really map out the entire distribution of the large-scale structure using those surveys, and then be able to then do inference on cosmology and galaxy formation physics. Just to tell us, starting with the galaxy, what we have learned from galaxy clusters, the previous generation of CMB experiment, like Atacama Cosmology Telescope, South Pole Telescope, Planck All-Sky Survey, they have detected thousands of galaxy clusters above 2 × 10⁻⁴ solar masses, and which has given us a lot of insight into cosmology and cluster astrophysics. And the next generation of survey like CMBS-4, CIMA Observatory, CMB-HD, they are designed to actually lower the math threshold, detecting clusters and protocluster at the high redshift, and promising to provide some constraints on cosmological parameter like W's, neutrino masses, testing inverted hierarchy in neutrino, exciting science that we can do by just detecting really massive clusters. In the X-ray side, they are very sensitive instruments. eROSITA, for example, have been detecting the smaller mass galaxy groups. These are results from EFES, the initial eROSITA data release. There are a lot more galaxy groups that's been detected well below, all the way down to 10⁻⁻13 solar masses, especially in the nearby universes, because X-ray becomes dim due to cosmological dimming at high redshift. These galaxy groups has been used to then provide constraints on cosmology. There has been a number of papers that's been coming out around over this year from the eROSITA ER1 data, providing interesting constraints on cosmology. But a lot of this, the future of this, utilizing this kind of observation, relies on our understanding of properties of baryons, especially those X-ray emitting warm hot phases of baryon that are detected in eROSITA, and are some of the main systematic uncertainty right now. It lies in our ability to characterize and predict what their properties might look like. So that's sort of a nonetheless, the statistical sample is extremely strong, and it will has already given us very interesting cosmological constraints, pushing the frontier in both cosmology and galaxy group physics. You can actually use eROSITA and stack the eROSITA pixels around the known galaxies from galaxy surveys, and you can actually detect these warm hot phases even around galaxies, even smaller galaxies, not even well below galaxy groups. And there are a couple of measurements that's being reported through the stacking measurements of eROSITA from Chadayamuri et al., Comparad et al. I think Erwin Lau, next talk, will talk a little bit more about how to model these emissions from CAMELS, especially also from the Jain et al., which has detected the X-ray surface brightness around some of these massive galaxies. So that's quite exciting. These are kinds of things that you can do by identifying the X-ray emission, SZ emission from halos, individual objects. You can use those and remove them to learn about cosmology and astrophysics. There are still additional signal in the remaining map. One can, for example, use the field level inference on the residual map. For example, one can compute power spectrum, which we have used to learn about the cosmology using primary CMB in the past. One can do similar analysis on the secondary CMB signal, like thermal SZ power spectrum, for example. Of course, there are a lot you can do once you have the maps of secondary CMB, because they are nonlinear and non-Gaussian, that one might actually want to use high-order statistics, want to do cross-correlation analysis, perhaps want to use simulation-based inference. There are many approaches that one can take to actually extract nonlinear signal that are beyond Gaussian statistics that can be captured by thermal SZ effect. So that's another additional handle that we can have on cosmology and astrophysics after identifying individual sources in these maps in CMB or X-ray. I think one of the exciting frontier also is the cosmic shear, how you can use the gravitational lensing effect, which causes the shearing effect around the background galaxies, and which then provide interesting constraints on this thing called S8 parameter, or S8 tension. S8 is a combination of sigma and omega matter. And in the recent measurements from HSC Y3 cosmology, for example, indicate some tantalizing possible tension with the primary CMB. The growth of structure seems to actually, measurement seems to indicate that the fluctuation in the present day universe is somewhat lower than what's predicted from the extrapolation from the CMB scales. And of course, this is one of the primary our target as a primary science goal for something like Euclid and many other optical survey. In order to actually do precision cosmology using this kind of survey, one really needs to have an accurate precision model of the matter power spectrum, how much power there is on various scales, and what's shown on the right-hand side shows the impact of baryonic feedback, baryonic effects on the matter power spectrum. What's shown on the right is the matter power spectrum in hydrodynamical simulation that has galaxy formation physics relative to the matter power spectrum in dark matter only simulation. And the latest simulation seems to predict fairly broad range of uncertainty on baryonic feedback. Some of the models are newer, some of the models are older. Nonetheless, the point is that there's no percent level convergence among the modern state-of-the-art simulation just yet, and this is the area that we really need to understand in order to understand the baryonic effect. Most of the baryons in the form of warm, hot phases in halos and also the intergalactic medium, and how baryons are doing, galaxies are doing feedback on those phases is impacting this, introducing these uncertainty that we really need to understand before we can actually use galaxy surveys to do cosmology or precision cosmology. Along the way, of course, we will learn tremendous thing about the galaxy formation astrophysics. So I think in terms of the warm, hot phases, we have been doing, in galaxy cluster, we can map out the distribution of dark matter, gas, and stars, pretty much the entire virialization region. We see everything. But I think probably one of the exciting frontier is to really go down to groups and galactic scale, where we don't see those warm, hot phases. In fact, only through the NASA cosmic origin spectrograph, through the absorption line studies, that we have been learning about those warm, hot phases. But over the next few years, as I would argue, that this is, I think, is one of the most exciting frontier where we can actually see those much of the baryon that has been missing. Not only we're interested in detecting them, we really want to characterize their properties and their impact on the cosmological signals. So this is the figure from the white paper that Nick Battaglia has led as a part of Astro 2020 Decadal Survey, which summarizes some of the new exciting frontier, starting from radio to CMB to X-ray, in addition to the absorption line studies that has been conducted using HST and various other measurements. So, and SZ effect is independent redshift, so you can stack SZ signal for any on galaxy survey and be able to detect all the way down to Milky Way size object independent redshift. In X-ray, it's sensitive because of the cosmological dimming that you can probably do through the stacking measurement I talked about. You can go down all the way down to about galaxy-sized object in the nearby universe, but not so much at the high redshift universe. I think what's really exciting in newcomer is a fast radio burst, which has been detected in abundance. The number of detection is exponentially growing. So this is one of the exciting new frontier for learning more about those warm, hot phases and their impact on cosmological tension. I think on the simulation side, there's equally exciting advances, and CAMELS simulation represent, I think, one of the major quantum leap in this area where the collaboration has been able to do many simulation while varying cosmology and astrophysics to really characterize, using multiple galaxy formation physics models to characterize how baryonic feedback have impact on observables. So this is a movie of the distribution of gas density in blue and temperature in red from multiple simulation that's being used to simulate in their fiducial model from Illustrious TNG, SIMBA, Asteroid, and Magneticum. There are more simulation that has been simulated in this way. This is just one of the few selected examples. And most of these simulations are designed to reproduce the stellar mass and halo mass relations. So galaxy properties in the local universe is supposed to be the same. And also the black hole mass sigma relation has also been used to calibrate many of the subgrid physics that goes into their original fiducial models. Nevertheless, when you look at the properties of warm, hot gas in these simulations, the impact of baryonic feedback is starkly different. For example, the SIMBA simulation seems to show strong ejective feedback, which blows out the gas and then the heat up pushes the gas out of the halo into the intergalactic medium, heating the temperature, homogenizing the universe. So if you look, for example, using FRB sight lines through many of these in various samples, in SIMBA universe, the dispersion measure from FRB would be constant across the universe, or it would be more or less similar because they have much more homogeneous density and temperature distribution because of the strong feedback. On the other hand, for example, if you look at the Illustrious TNG, Magneticum, or Asteroid, the universe looks a lot clumpier in warm, hot phases. So if you take a sight lines with FRB through these images, you expect to see significant variation from sight line to sight line depending on where you are actually looking through. So you expect to see larger spread in dispersion measure, for example, using FRB as a probe. Nice thing about these simulations is that you can then compute observable. You can now start to look at distribution of X-ray surface brightness, X-ray emission, properties of galaxies as a function of cosmology in sigma 8 on the top, as a function of a supernova energy feedback, AGN energy feedback, and you can then make a predictive model of observable universe, or these warm, hot phases in particular. So for the first time, you can actually do this kind of prediction and then also study how the observable, like galaxies and gas, depends on these cosmological astrophysical parameter. And this is important. Another interesting development here is the impact of baryons on the matter power spectrum that I talked about earlier. This is the work from Matt Gebhardt, which indicates the impact of baryons on the matter power spectrum, the same plot that I showed earlier, and that the energy feedback, especially distinct of baryon spread. Stronger the feedback, you spread more baryon relative to the original dark matter position, and they seem to have control the impact of baryons, which is a very nice demonstration. It's been shown a few times, but this is a nice way of showing that using CAMELS simulation for a wide range of cosmological astrophysical parameter space. What is really important for the cosmic shear survey is this idea of baryon spread. Stronger the feedback, more ejective the feedback, you spread the baryon relative to dark matter position, and that determines the amount of feedback that you have on the matter power spectrum. So it's nice that in simulations you can actually quantify what is responsible for this baryonic effect that we need to calibrate over the next few years. The only issues with the baryon spread is that it's something you can measure in simulations. I think it's also useful to actually look for ways to observe that baryon spread. This is a talk that I think Isa Medlock will talk about later this afternoon, that there has been a search of how to find this observable proxy for baryon spread metric. And in fact, this thing called F parameter, which I will refer to Isa's talk, seems to actually measure the amount of energy feedback of baryon spread. There is, in fact, available from a fast radio burst. This has to do with this dispersion measure of dispersion, the dispersion of the dispersion measurements. But I think and then in fact, if you use this F parameter in FRB, you might, regardless of the galaxy formation physics, that this relation seems to fall on the same curve. So for our universe, we can measure what the baryon spread and therefore the impact of baryons on the matter power spectrum using FRB as a probe over the next few years. The other things that one can do is to use X-ray and SZ. There has been some effort in developing emulators for emulating X-ray and SZ sky, especially those warm, hot galaxies, from Moser et al. For SZ modeling, Lau et al. From the paper that was posted today on modeling X-ray. And you can you can emulate the profile of X-ray surface brightness profile and Compton Y profile as a function of radius, as a function of cosmology and astrophysics. And then you can emulate what that predicted X-ray or SZ signal should look like. You can paste those halo profile onto n-body simulation, and you can also emulate the sky. So you can then also do field level inference using those simulations that are created using CAMELS emulators as a way of creating mock skies. One issue with emulator approach is that we can emulate the universe for TNG universe, Simba universe, Astrid universe, Magneticum universe, and so forth. But I think there's some issues with sort of interpretability because we can emulate any given universes, but probably not in between. We like to also know some other universes that might fall in between those particular model predictions. So one of the effort that we are also exploring is to see if we can write down a simple analytical model that captures the effect of feedback and also perhaps the effect of non-thermal pressure, turbulent bulk motion that are generated by the accretion process or the AGN feedback. And as long as we identify specific processes that we can model and their impact on profile, then we might be able to capture some of those effects as a function of these feedback strength using analytical models. So in this effort, that led us to actually compile and do the comparison of analytical models of circumgalactic medium from precipitation model, isentropic model, cooling flow model, baryon pasting model. There are a number of models that are out there that makes different assumptions for different reasons. And doing these comparison projects and trying to capture, eventually calibrate this using simulation. When you turn up the feedback strength to mimic the ejective feedback in Simba, you should be able to reproduce what we see in Simba universes. If you dial that back down a little bit and then reproduce, trying to tune the feedback processes to match what we are seeing, effective feedback in TNG simulation, you should be able to then see that model. So in this way, we're trying to generalize the write down sort of simple ansatz that will hopefully capture some of the features that we're seeing in specific simulations. Now, once you have that kind of analytical model, you can then use this as in the halo-based modeling and compute the map level statistics like auto spectrum, cross spectrum of multi-wavelength survey, X-ray, SZ, and also lensing. And then because these parameters are, the models are parameterized using fairly simple model, like amount of non-thermal pressure in bulk and turbulent motion, amount of stellar mass-halo mass relation, amount of feedback, amount of substructure that might boost the X-ray signals. All of those are simply parameterized that you can then study their impact on the map level statistics. So this is the kind of things that one can do, and using this kind of model, one can also do the power spectrum analysis from X-ray EFEDS measurements on the left, and then the ERAS-1 measurement, 1-year data on the right, where you can then extract the SA constraints on, and so even using the simple halo model, one can actually use this to extract interesting cosmological and as well as the constraints on astrophysical signals in galaxy groups. And you can also do the forecast, and this is the expected forecast when you use the halo model and then trying to actually constrain cosmology and astrophysics using Eurosita CMBS4 and Rubin. And you can constrain non-thermal pressure profile from X-ray and SZ. The gas clumpiness is particularly impactful in X-ray. And then you can break degeneracy of those galaxy group astrophysics and then derive constraints on cosmology. So this is the kind of pipeline that we wish to develop, but make sure that we are doing this in a way that is physically sensible and interpretable and explainable. One can actually take those profile models, paste it onto very large n-body simulations. In this case, the example from Uchu simulation, and then that you can create the half-sky map of X-ray surface brightness, thermal SZ effect. Instead of assuming that everything is spherical, I think one of the key areas in the future is to model scatter. Intrinsic scatter, halo-to-halo variation in X-ray and SZ surface brightness that depends on accretion history of the halo, as well as impact of feedback, as well as extrinsic scatter. The fact that the halos are elliptical and triaxial, they also produce some scatter in the observable depending on how they get projected. So in this model, one can then quickly change spherical halo, elliptical halo, intrinsic scatter, all of those are taken into account, and we can see how that impacts the observable. These are one of the main sources of biases in those future survey when we go to precision levels. The other thing, frontier, is to actually forward model these covariances among different features. This is a correlation of profile of dark matter and gas profile, dark matter and stellar profile, stellar and gas profile. Based on the illustrious TNG simulation, what we see is the gas follows dark matter reasonably well in the outskirts, as we predict, especially on high mass objects. However, if you go to lower mass object where potential is smaller, AGN has bigger effect, or the supernova has bigger effect, so the sphere of influence of the baryonic effect increases, and then there's a decorrelation effect. Basically, these feedback is randomizing these gas, causing decorrelation of dark matter. Gas is now puffed up, and they also don't follow the dark matter halo. So these are kinds of effects that we need to actually model. And these covariances, each of those dark matter, gas, and stars goes into modeling various observables in multi-wavelength observations. So the future is then to actually model the X-ray surface brightness sky as a function of feedback, as a function of non-thermal pressure. So this is a work in progress. We're trying to make sure that for example, intrinsic scatter has impact on power spectrum. The extrinsic scatter creates the impact biases in selection function. If the gas is oriented along line of sight, or halo is oriented along line of sight, you get boosting effect in X-ray. So all of those shape information would have to be modeled in. In fact, there's a large scatter, we know, in galaxy groups, and also likely in galaxy-sized halo, that all of these scatter has to be modeled precisely. So this is one of the new frontier that we see, and we can also do similar kind of painting. We can baryonify the lensing map and galaxy survey from Rubin, and trying to do multi-wavelengths analysis. Really bringing all of those multi-wavelengths data is the way to go for constraining the galaxy astrophysics, and then eventually to enable precision cosmology. I will just mention in the last slide that we also, so far I talked a lot about halo-based modeling, but the impact of baryons outside of the halo is particularly important for some of the exciting observations like KSZ, kinetic SZ effect, and FRB. They get contribution from outside of the halo, so halo model is a limited tool that assumes that all of the mass signals are in the halo. That's not the case for KSZ and FRB. Halo model works reasonably well. One can also do pasting based on particle data, and you can get these aspherical shape of the halo as well as the IGM modeling. But on KSZ, the map is very different, whether you actually model gas in the halo or not. So, however, this particle-based pasting is order of magnitude slower. So in order to do that cosmological inference in this high-dimensional parameter space, we really need to accelerate this. The next step is to actually create this go beyond halo model. We want to also want to model filament, how that depends on cosmology and astrophysics. So we're looking very carefully into the details of filament models, and then hopefully we can extend the halo model to then do the modeling of large-scale structure and be able to do inference in the fast enough speed so that we can actually get cosmology and astrophysics at the same time. So maybe I'll just end here that I think we're really entering into the golden age of cosmology and galaxy formation astrophysics, and I think those large set of surveys and simulations are really giving us all of the tools that we need. And I think we need to find a way to synthesize. There are a couple of wish lists here that will be useful for advancing this field over the next decade or so. So thank you very much.
Thank you, Daisuke. We have about, well, I'm blind here. I think a couple of minutes for questions. So are there any questions from the audience? Yes, please, go ahead.
You have talked about a lot because the feedback is affecting the gas. A lot of gas observation, how they affect the gas. I wonder that if there are any investigate into galaxies, right? And how the galaxy can be strongly affected by the bion models, etc.
Absolutely. That's very much ongoing. The galaxy properties are affected by those feedback. And so,
not this one.
But one thing I should mention is that in the fiducial model, many of the galaxy properties are pretty reasonable because it's designed, it's calibrated to reproduce stellar mass-halo mass relation. Yeah. But when you actually change the parameter from the fiducial model, then it will have a significant impact on galaxy properties, which would make the galaxy model somewhat unrealistic. But that's we really want to use both galaxies and gas observations to actually then constrain the uncertainty in galaxy formation physics. So yes, I think it has a huge impact.
Okay, great. Thanks. Very nice talk, by the way.
Yeah, thank you.
Any other questions? Any questions from Zoom? Check. So please go ahead.
Can you hear me? I don't know how it works. Yeah, very nice talk. So I'm just curious about for the particle phase painting and the halo phase painting, you mentioned that the KZ and FRB are particularly affected, but have you checked the meta-pulse spectrum in those marks and see whether the meta-pulse spectrum is also
we have different? Not. We don't have a realistic model of filament as a function of feedback physics, nor cosmology just yet. We are looking into million TNG simulations to calibrate that model. We are very much working on this topic as we speak. So we have a halo model that, that as a function of cosmology and astrophysics. I think it's pretty well calibrated thanks to CAMELS simulations. But doing this for filament is very much the ongoing process. So, but hopefully we can have this in the next few years.
Thanks.
So let's thank Daisuke again. Thank you. And can the next speaker... Thank you. Yes, so next we have Erwin Lau talking about X-rays and CAMELS as well.
Hi, everyone. Thanks to the organizer for this exciting conference. And I'm going to talk about a paper that is submitted to arXiv last week and appeared last night on constraining CGM physics with CAMELS and the X-ray data from the Rosita All-Sky survey. Okay. Yeah, so a bit background about the CGM, or the circumgalactic medium. It's basically the gas surrounding massive galaxies. It's massive galaxies meaning like Milky Way galaxies, Milky Way mass galaxies also. So the CGM, at this mass scale, the CGM sits at the sort of flux between stellar-dominated feedback and AGN-dominated feedback. And it provides a wealth of information about galaxy formation, because the CGM will tell us about gas inflow, star formation, feedback and outflows, and also matter enrichment and chemical evolution. So this is just a schematic showing where the CGM sits between the stellar-dominated and AGN-dominated feedback, and what the current state of simulation showing the scatter around the stellar mass-halo mass relation. So one of the exciting development in the past year and earlier this year is the release of the Rosita All-Sky survey. So it's a Russian-German X-ray mission that is supposed to scan the whole full sky. And so far, before the war broke out 2 years ago, it managed to scan 4 full sky, have 4 full sky data. So and each full sky data have average about 100 seconds, so it's not really that much, but it already gives us a very new view about galaxy formation physics as well as cosmology, as Daisuke just mentioned earlier. And so the first Western galactic half sky, the German half, has been released earlier this year, and it already contains so the largest number of X-ray sources that has been detected so far, meaning that combining all of the X-ray sources from Chandra, XMM, Rosette, and all those data that has been detected before the launch of Eurosita. Eurosita has like what they detected already exceed all of them combined. So with this, we can do something to investigate X-ray CGM of individual of galaxies. So the CGM, the X-ray emission of CGM is intrinsically very dim because of the sort of lower temperature than groups and clusters. So to do that, stacking is a very nice way of increasing the signal to noise. So here I'm showing the paper from Miller that uses the stacking method to increase the signal to noise ratio of X-ray emission from galaxies in the small patch of sky in the Eurosita, the EFATS sample. So yeah, showing basically they divided the sample into 4 bins, low star in terms of sand mass and in terms of the star formation rate. So however, these some caveat about this stacking procedure is that it's still sensitive to some of the contaminants, like from X-ray binaries, from background point sources like AGNs, and also emissions from galaxy groups that could go into your stacking measurements. And because you're also stacking across a sort of over some samples of galaxies, you're bound to have some few outliers that may bias your stack measurements. And finally, Eurosita has a relatively large PSF, so point sources may not be accounted for as bad as one would want to have. So this is some systematics that has to be kept in mind when I discuss a comparison with CAMELS and Eurosita measurements in the talk. So this is the Eurosita measurements from Jain et al. 2024 that shows the X-ray surface brightness profile for 3 stellar mass bins. So they use the SDSS main galaxy samples, which also contain spectroscopic redshift to do the stack measurements. So they choose like stellar mass of like three main stellar mass, the Milky Way stellar mass, the M31 stellar mass, and the 2 times M31 stellar mass, which is like higher stellar mass than M31, as 3 main samples that they use to stack the X-ray emission on. So this is the measurements, and they have a way to model contributions from contaminants, from AGN, from X-ray binaries, and from satellite galaxies. So shown in this orange band here. And after subtracting those model, the purple points and the shaded regions indicate what they think is the X-ray emission from the CGM. And the red line is just they try to fit a beta model to that. So we're using these measurements to compare with the simulations. And in addition to the X-ray surface brightness profile, they also measure the X-ray luminosity stellar mass relation. Again, they're using the SDSS galaxy sample to do the stacking, and they measure the X-ray luminosity for those stellar mass bins. And you can see that the purple point here is the stack measurements. And the gray lines and gray shaded regions indicate the same LX M-star relation for different simulations. For example, the dotted line is from Eagle, the dash line is from TNG 100, and the dot dash line is from Simba. And you can see that there's a wide range of differences between the ERAS measurements and the simulations. if you compare, say, the difference between the simulations and the statistical error bar of the stack measurements, you see that the difference are much larger than the statistical error. So this shows us there's some kind of mild tension between the simulations and the ERAS observations. And how can we reconcile this? CAMELS is one of sort of comes to the sort of rescue because with CAMELS we have a large range of simulations with different feedback physics, and we can study whether we can reconcile these difference in the simulations and observations with varying feedback physics. So with CAMELS, we generate emulators using the legend hypercube set of the CAMELS run for the Lester's TNG, the Simba, and the Astrid runs. So we emulate the X-ray surface brightness profiles and also the X-ray luminosity mass relation from all of the three simulation suite. And we explore the effects of feedback due to supernova and AGN, how they vary the X-ray properties in the CGM halos. So just to sort of going through the feedback parameters that we study, we have two feedback parameters from like supernova or SLAB feedback that represent so SN1 represent the supernova energy output per unit star formation rate, and it also represent the mass loading factor for the Simba run. SN2 represent the wind speed of your stellar feedback, and for the two AGN feedback, it represents the kinetic AGN feedback for Lester's and Astrid, and also it represents the jet momentum flux for Simba. And for the other AGN parameter, it represents how frequent the AGN is going off in TNG, jet speed for Simba, and the thermal AGN feedback for Astrid. And we indicate the range of value that has been explored in the average set. And the value of 1 indicates that these parameters are like the foundation model that's used in the original TNG, Simba, and Astrid simulations. So let's look at the comparison first between the TNG and the ERAS simulations, ERAS observations. So here I'm showing again the 3 stellar mass bins that the ERAS people has measured, compared with the X-ray surface brightness profile from the TNG ones from our emulated profiles. The red color shows the stronger feedback, and the blue color shows the weakest feedback. And the dashed line shows the foundation model where all the feedback parameters are set to 1. And you can see that increasing feedback it increases the X-ray surface brightness, and that's basically because if you increase the supernova feedback, you're increasing the gas density. That's by limiting the amount of gas that's accreted onto the supermassive black hole in the halos that actually stops the gas from blowing out due to the feedback. So it raises the gas density, and as the X-ray emission is proportional to the gas density squared, so you get a higher X-ray surface brightness because of that. On the other hand, if you compare the AGN energy, it doesn't show as much of a dependence. Essentially, if you change AGN energy, it doesn't really change the X-ray surface brightness profile much. And if you change the AGN 2 parameter, in this case, the TNG is the burstiness, it also has a very weak dependence. The X-ray emission has also a very weak dependence on this AGN parameter. And we can look at the X-ray luminosity mass relation. It tells us basically a similar story. If you change the supernova energy, it changes the X-ray luminosity for a given stellar mass by quite a lot. If you change AGN, the X-ray luminosity is less dependent on that. So one thing to note that is that the relatively weak dependence on HN could be due to the relatively small number of massive halos in the 25 megaparsec box of CAMELS. So showing one of the things that we would like to do in a near future is to look at the larger box to see how that affects how we can understand the effect of AGN onto the X-ray luminosity. So when we look at the SIMBA run, SIMBA on the whole, it generally underestimates the X-ray luminosity due to the gas that has been sort of blown up by the jet feedback implemented in SIMBA. So if we lower the supernova energy, it actually gives us a high X-ray luminosity for a given stellar mass. On the other hand, if you increase the wind speed, it has the opposite effect. But similar to TNG, the SIMBA run also depends. The X-ray emission from SIMBA also depends more on the supernova energy, supernova feedback than the AGN feedback. And for the asteroid run, it's similar, but it's also different in that the asteroid Fidesian model of asteroid it generally overpredicts the X-ray luminosity for a given stellar mass, and it's very sensitive to supernova energy and also the thermal AGN feedback, the CAGN2 here. And for this AGN feedback, you can also see a non-monotopic behavior in that if you increase the AGN feedback up to a certain point, it actually decreases your X-ray luminosity. And we can understand that with the having too strong thermal AGN feedback, it actually puffs up your gas too much and lowering the effective gas density that leads to a lower X-ray luminosity. So with the very exquisite statistical error from the ERAS measurements, we can actually do some sort of constraints on the feedback parameters of these three different simulations in CAMELS. In general, the ERAS observations prefer a stronger supernova and supernova 1 and AGN1 parameter, meaning that they prefer a stronger supernova energy and AGN energy. But in general, it also prefers a lower SN2 and AGN2 parameters. So this shows, again, I'm showing the best fit parameter compared to the ERAS observations. It shows pretty good agreement. So if we take these best fit parameters and we put it back into the simulations and predict the stellar mass halo mass relation, what do we get? So the best fit parameters actually leads to a quite different stellar mass fraction as indicated in the plot here. So the dotted line here is the empirical fit of the stellar mass halo mass relation or stellar mass fraction from observations. And the three different lines, solid lines, indicate the stellar mass fraction from the best fit feedback parameters from the ERAS measurements. And we see that they are quite different. For example, for TNG, there's agreement at relatively high mass halos, but below like 10 to 12 solar mass, you see a drop in the stellar mass fraction, and that's because of because ERAS prefer a stronger supernova feedback that leads to a stronger quenching of star formation. That leads to a drop in the stellar mass halo mass, drop in the stellar mass fraction at the lower end of the mass spectrum. But one caveat is that here we assume the ERAS observation is they did a accurate job of accounting for potential contamination, which might not be the case. So, for example, if the ERAS observations haven't been able to take care of potential contamination from, say, X-ray binaries and background from groups, that could lead to an overestimate in the X-ray emission. So if we account for those extra contaminants, that would bring the actual X-ray emission, observed X-ray emission down. That would actually lead to a better agreement with the fiducial models of the CAMELS simulations. So this tension could be evaluated with maybe with a better accounting for potential systematics and observations. So some take-home message and so conclusion is that the data from EROS-CETA enables us to put actual constraint on the CGM feedback physics, I guess maybe for the first time. So that's exciting. The EROS observations prefers a stronger supernova and AGN feedback energies in these 3 modern cosmological simulations that we have investigated so far. And we show a possible tension in the resulting cell mass fraction between the best fit, the EROS inferred best fit result with the fiducial cell mass fraction from these simulations. And if we take care of contaminations, this tension could potentially be alleviated. And with future work, such as if we have high resolution X-ray observations from Chandra and XMM, which have very high angular resolution, we may be able to better account for contaminants such as AGN and star-forming galaxies on X-ray binaries that are point sources. And with SZ, which are insensitive to all those contaminants, it will also give us some clue on how to explain these or how to alleviate these tension. So I'll leave it at that and I'll take questions.
Thank you very much, Erwin. Any questions for Erwin? Please go ahead.
Have you looked at whether or not how this agreement looks as a function of redshift, or disagreement looks as a function of redshift?
No, we haven't, because one of the reasons is that the EROS observation they are confined to low redshift halos. Okay. So we haven't looked into, well, we don't have the data for high redshift from EROS. So the redshift is like between 0.1 to 0.2. So yeah, so we welcome any if there are high redshift X-ray observations, that would be great actually. Yeah.
I have a question from Zoom.
Yeah, we have a question from Ben Oppenheimer. So it seems like varying more astrophysical parameters is necessary to find a fit for X-ray and galaxy properties. Will this emulator work on the SB28 larger CAMELS suite where over 20 astrophysical parameters are varied?
Yeah, so we are working on the SB28 set, which have expanded set of parameters in terms of astrophysics and also cosmology. So we are working on that, and the emulator framework that we used in this ARIC set, which only have 6 parameters, it doesn't work perfectly. So we are working towards a better way of doing the emulation for this 28 parameter set. So that's very much in progress.
Question over there, please.
The discrepancy between in the stellar mass plot was very large, more than an order of magnitude below 10 to the 12. So does the X-ray binary contamination, will it bring it down that much?
That's something that I want to know. I don't have a good answer to that. So yeah.
Yeah, from the previous row, please.
So you have mentioned from CAMELS that you vary the aging feedback. There is no much dependence. There is, for either model, you can see that is almost no change in the X-ray luminosity. Yeah. But think about the aging is supposed to be the strongest feedback. Yeah. Do you have any idea why it's looking like that?
Yeah, so So this result actually indicate that the more pronounced effect due to supernova, the supernova parameter rather than the AGN parameter. It tells us that what controls the AGN feedback is actually the supernova, when you vary the supernova energy. So varying the AGN energy itself, it has a less effect. So when you vary the supernova energy, the main effect is it limits the amount of gas secreted onto the black hole. So this is a reflection of this effect. So varying supernova energy, so it indicates that the amount of gas that the black hole is able to accrete has a stronger effect than varying the energy output.
Okay, thanks. Yeah.
And time for one last question at the back, please.
Do you think this sensitivity would be different if you had the bigger boxes, the next generation bigger CAMELS boxes, maybe?
Yeah, so I would hope that having a bigger box with more massive halos or bigger variation in the, with maybe like a larger dynamic range of halos in terms of both halo masses and also supermassive black holes. I think that will be useful to like understand this effect. Yeah.
Thank you very much, Erwin.
Yeah, thanks.
And can the next speaker, I think, is Bhuvnesh Jay? Come up, please. Thank you. So I think the time might not be right when it comes up, but I can let you know when you have 5 minutes left.
Okay, we'll change it.
Next, we have Bhuvnesh Jay talking about higher order statistics for weak lengthening. Thank you.
Thank you. Sorry. Hi, everyone. Great to see you all. I'm giving a talk on weak lensing. There are some great talks ahead today and in the coming days. My primary collaborators are 2 brilliant graduate students who are in the room, Min-Soo Park and Kun-Hao Zong, and Marco Gatti, who was a postdoc at Penn and is now at Chicago. And I'll show some results from the dark energy survey. Since it's the first talk on lensing, this is a cartoon showing unlensed galaxies and what a galaxy cluster would do on the right. I'm talking about large-scale cosmological lensing. The effect is much weaker, 1,000 times weaker. And what I'll be talking about is 2-point and higher order correlations. So this is the DES mass map, work led by Niall Jeffrey and Marco Gatti. And so this is approaching 5,000 square degrees using 100 million galaxies. And you can see the hot and cold spots, namely clusters, superclusters, and cosmic voids. So to analyze this map, usually people use 2-point correlations. Our primary results are based on those, but there's also a whole universe of higher order statistics, because if you stare at this map carefully, you can see it's not Gaussian. It's not symmetric between blue and red. It has extended structures. It had some anisotropy. It's projected, so it's much weaker than galaxy 3D redshift surveys, but there's clear information beyond 2-point functions. I will talk mainly just about wavelet-based statistics today, and then I'll move on to 2 cute ideas that are squarely in the machine learning realm. So this is a paper by Sihao Cheng and Brice Menard that shows quite beautifully how going from microscopic to the macroscopic scales of cosmological lensing maps and the solar surface in between, a variety of these hierarchical naturalistic patterns that also have in common that they're stochastic, they're very well captured by wavelets. So there's various families of wavelets, blah, blah, blah. But it's been known for a long time that they have very nice properties. They strike a balance in compactness in real space and Fourier space. And so these authors showed an implementation called scattering transform. We were persuaded by this paper and by another one that talks about wavelet phase harmonics and adopted these wavelets as our favorite higher order statistic. I shouldn't have said that. I spent like too many years of my life pursuing three-point correlation functions to abandon them so quickly. But this is another reason why wavelets are so nice, that the covariance matrix is really nicely band diagonal for this particular wavelet phase harmonic. And this is the opposite. If you take moments, then you barely have like two uncorrelated bins. So I'm going pretty fast through this part of the talk, just to point out that when we combine a simple third moment and wavelets, then Marco Gatti led this work, a methodology paper and an application to DES paper, where we believe we have a really robust simulation-based inference implementation that's good enough for data today. There are a lot of simulation-based studies, but we're starting to see applications to data that actually look pretty believable, and I certainly believe this one that we did. You know, you can gain about a factor of 2 in the figure of merit when you look at WCDM. It's a bit less in LCDM. And this result is in 2 sigma tension with Planck. We also have, you know, going to the other extreme, this is mixing up, this is like using 4 different higher order statistics and combining them. If you've seen the Euclid paper, that's like the limit of using a dozen different higher order statistics with no guidance on what the hell to do when you have that many. Not a criticism of the Euclid paper, that's just the state of the field. So we made our judgment call, but we're also doing a full shape 3-point analysis, and the methodology papers, you know, in final stages of review. And we are finding it's pretty powerful when you add up all the triangles. So not quite this powerful, but powerful. This is a transition joke slide. There's a lot of really beautiful theoretical simulation-based papers that show factors of 4, 5, 8. I'm not sure about 10. Whenever you apply a higher order statistic to data, you gain between 20% and factor of 2. So is the integer 2 an upper bound? Obviously not, but consider this a challenge. This theorem may be, you may see a counterexample at this meeting. That would be great. But I haven't yet seen one in the literature. And this is a statement of my personal sadness, that why does weak lensing give a 2 sigma tension? And as the error bars shrink, why does it not get to 3 or 4? Of course, some people believe it's not 2 sigma either. But anyway, I just don't know. Is there, you know, do photons behave differently from non-relativistic matter? Of course, you know, you just need to shift photo z's by 0.1 and everything goes away. And there's other resolutions you'll hear about, maybe from Alex. But I'm going to leave it there. Happy to discuss over kombucha or your favorite drink. So I want to tell you about these 2 advances in machine learning. I've set the stage for my personal humility already, whether it's cosmology or politics. It's like a moment to step back and say, let's forget about the big stuff and, you know, what is the small thing I can do better? So I'll show you 2 advances that I think are pretty useful. So one is based on this paper led by Kunhao, where I'll just jump to the map. Okay, so this is a little bit of magic if you're in the mood. So this is a lensing map produced by full-on N-body simulations. And this is a map that Kunhao generated using a simple function. And if you look closely, you will see the patterns are generally pretty good, almost indistinguishable. If you stare at it with your laptop, your eye will pick up subtle differences. Our claim is LSST will not. So that's why I'm talking about this, that we think we have an analytical way to generate nonlinear maps that are good enough for the next decade. Very bold claim. But really, it's meant to be an aid. We think these maps will aid simulation-based inference in many ways. One thing Kunhao has done is he's fine-tuned the CNN using just millions of analytical maps he generated on his laptop, immediately boosted the performance. So that was kind of a proof that CNNs in cosmology today have not actually saturated all the information content, partly because we don't have millions of simulations to train them. You can also think of it as an embedding vector, in the ChatGPT era. All of cosmological weak lensing is represented in a 5-dimensional embedding vector by a 5-dimensional embedding vector. All the initial power spectrum, gravitational evolution, unknown cosmological parameters, that's what it all amounts to. So pretty interesting to think about. There are various caveats that I could add. The main one is that this is valid for a projected map like weak lensing or some X-ray or SZ maps with a smoothing scale of 5 arcminutes or larger. On smaller scales, you see that you need to do better. All right. So how does this work? Many of you are familiar with the log normal transformation. So this is the PDF of a cosmological field, in this case the lensing convergence, going out very far into the tails. So you can see we're going orders of magnitude down in the PDF. And of course, a Gaussian, which is the blue, fails very quickly. A log normal fits this region reasonably well, but fails on both sides. So Kunhao's idea was very simple. Well, the log normal is really cool, but I know how to fit more complicated functions. And so he went up to a 5-parameter function, and he got an important help from symbolic regression, because symbolic regression used a term we would never have thought to use. And so he came up with a 5-parameter function that fitted this PDF much better. And the way you do it is you construct a cumulative distribution function. You don't need to look at the plot or the equation. The idea is easier to understand just in words. You take your skewed probability distribution, you make a cumulative distribution function, you match it to a Gaussian, and that gives you a 1-point transformation between your map and a Gaussian map. There's one other trick that you may know from log normal functions, that once you've done the 1-point transformation, you can think of it as you have the freedom to move matter around to also match the power spectrum. So any of these analytical functions can match the power spectrum exactly. And the approximation that turns out to be super valid is that, in fact, once you do this, all the higher order correlations work out. For the log normal, they fail immediately at the 3-point level. For Kunhao's function, they work. So this is the function. I'm not inviting you to stare at it, but it's a mix of exponential and linear terms with 5 free parameters, only 3 of which actually matter. And I'll explain in what sense. This is one of the many statistics that Kunhao presents in our paper. This is just the PDF, and the red curve is his fitting function The blue is the log normal. The gray band are the LSST, full LSST error bars. You can see we're going out very far into the tails. Most of the action is actually here, where you can zoom in and see how well it does. But 3-point functions, peaks, all kinds of wavelets, Minkowski functionals. He has also implemented tomography, so in different redshift bins, the maps are correlated right. So the idea is very simple, the function is very simple, implementation takes a little work. But once you've done it, you have this magic in your laptop that you can generate maps. So of course, you can build even better emulators, right? So why do you want to build this one? It's all related to the speed and the analyticity of it. So you can generalize to different cosmologies. You can interpolate in parameter space. And you can be much more confident you'll avoid overfitting, rapid covariance estimation. This is, sorry, how am I doing on time? That's the time left? Okay. Let me move on then. We're also pursuing a diffusion model approach, and we don't have a paper yet, but Supranta's in the audience, and would, there's a lot of fun stuff to talk about there. My second topic is dimensionality reduction, where Minsu had an equally brilliant insight. He first found, just as a routine exercise in checking, he found that all the state-of-the-art stuff we use, moped and neural nets, in standard implementations are actually quite lossy. You wouldn't want to lose 30% on your figure of merit because you compressed your data using a lossy method. And in fact, we are just reaching the point where, especially in lensing, data compression is essential, because when you have 4 tomographic bins, your data vector is approaching 1,000 elements already for higher order statistics especially. So Minsu came up with a variation of moped and discovered a method in the literature called canonical correlation analysis. We didn't find this method because we are giving a talk at CCA, I promise. And these two methods find this balance between using compression, using the variance in the data itself, and using compression because you really want sensitivity to parameters. So PCA uses just variance in the data, knowing nothing about parameters. And moped does parameters, but only, and practically speaking, it evaluates derivatives at the fiducial cosmology. So you need to waste a ton of simulations at your fiducial cosmology. So Minsu's variation eMoped for easy moped does a linear translation of all the available simulations so that they can be used to do moped. And CCA is kind of an information maximizing approach between the data vector and the parameters. So these two methods that we propose in this paper actually perform really well. This is a CCA in the dark band. This figure is not that impressive, but there's 30% or so in the figure of merit. And for 2-point functions and a bunch of higher order statistics, quite robustly. For current weak lensing data, we find these linear methods actually are the methods of choice, even including neural nets, unless you have infinite simulations. He also found 2 other non-intuitive things. One is that you don't want to go all the way and say, if I want to learn S8 and omega matter, I should compress my data to 2 numbers. You will lose out. You do want more than a dozen elements in your compressed data vector. And you do want to compress 2-point and higher order statistics separately. In retrospect, fairly obvious why one should do these things, but read our paper. Then looking ahead, Minsu made this toy plot where I'll just show this panel. If you're in the linear low noise regime, namely your data vector responds linearly to variations in parameters, the linear methods are better. If you're in the nonlinear low noise regime, so he made up a highly nonlinear dependence of the data vector on parameters, then with enough training data, neural nets will outperform. But weak lensing cosmology is not going to be in that regime for a while. We don't yet know of a data vector that has such a nonlinear dependence. All right, I will wrap up there. Thank you very much.
Thank you, Bhuvnesh. Any questions? Yeah, Paco?
Yeah, so very nice talk, both. So I was wondering, so I'm very impressed, but basically you feed the PDF with this functional form, and then you say that you get all the higher order statistics.
Yes, we fit the PDF. We are guaranteed to reproduce the power spectrum, and we find that we get all the higher order statistics. One way to say it is that when we Gaussianize this field, then when you apply a one-point transform and you get a one-point PDF that's Gaussian, that's not a Gaussian random field, right? It turns out it's pretty close. Like I said, the caveat is projected maps have already taken out some non-Gaussianity through projection. And so projected maps on scales above a couple of megaparsecs, this works.
But then if you compute the covariance matrix between the PDF and all these other higher order, then they have to be very correlated. Because otherwise, how can I understand? Or other words, like the PDF contains all the information in these formalies.
That's correct. The PDF on the right scale plus the power spectrum, yes, that's right. That's right. A little surprising.
Yeah, go ahead, Daniel.
Is it possible to include the impact of baryonic effects in this formalism?
Great question. Another caveat I didn't mention. All the systematics you deal with in the usual way. If you want to baryonify, like if you have a baryonification type recipe for lensing maps, you can apply it to our analytical maps. IA, you can implement. But anything you can do with lensing maps, you can do. If you've got to go back to halos and embody, then our stuff is not useful.
Yeah, please, John.
Thanks a lot. Yeah, and just following up on that, you mentioned that this like 5-point stochastic process form could be used to later fine-tune methods like CNNs and stuff like that. I was curious why you wouldn't want to just directly forward model it using this form, unless I've missed something here.
Great question. We are not that brave, but in fact, Kuhnhao tried it. So he trained a CNN on this, and then he gave the CNN a real n-body map, and he found that it works pretty well. In fact, the figure I didn't have time to talk about showed that. But he also found that if he fine-tunes with this, if he pre-trains with this and then fine-tunes with n-body, he gets a little better performance. Yeah.
Well, let's thank Bhuvnesh again. Thank you very much.